Unit 2, Chemical Reactions. A chemical reaction is a process in which one or more substances change into one or more new substances. We can write chemical reactions in word equations. For example, hydrogen peroxide decomposes with the help of the catalyst, manganese dioxide, to form water, oxygen, and energy. We can also write the same chemical reaction as a chemical equation. H2O2 produces, with the help of MnO2, H2O and O2. Notice that there are coefficients in front of some of the molecules. These coefficients are there because of the law of conservation of mass. And the law of conservation of mass states that during a chemical reaction, the total number of mass of the reactants equals the total mass of the products. So the total mass of the reactants must equal the total mass of the products. In order to determine whether coefficients are necessary, we have to learn how to balance chemical reactions. The following, this one, is a balanced chemical reaction. The rules for balancing chemical reactions or chemical equations are as follows. Number 1, start by writing a skeleton equation. This includes the chemical formulas without any coefficients. Number 2, balance atoms that appear only once on each side of the equation by placing the appropriate coefficient in front of the chemical formulas. Number 3, leave atoms that appear more than once to the end. Number 4, treat polyatomic ions as one unit rather than as individual atoms, provided that they don't change during the reaction. And number 5, check that the final equation is balanced. Leave hydrogen and oxygen to the end, except in the case of combustion reactions. Let's start by trying to balance the equation for the reaction between sodium and oxygen, producing sodium oxide. We're going to look at sodium first. This is an element that appears only once. Now, oxygen appears only once as well, but we're going to leave it till the end. For the reactants, sodium and oxygen, we see that there is one sodium for the reactants. But in the products, we see that there are two sodiums. The number of sodium in the reactants must equal the number of sodium in the products. In order to make this balance, we're going to have to use a coefficient. I will place the coefficient 2 in front of the sodium. So now there are 2 sodium in front and 2 sodium in the back, or the products. Now let's look at oxygen. In the reactants, we see that there are 2 oxygen. And in the products, there's only 1. In order to make these balanced, I have to place a coefficient 2 in front of the products. You would multiply this coefficient by the number of oxygen. So now there are 2 oxygen present in the products. But doing so has changed the number of sodiums, because if you're multiplying the coefficient by the number of oxygens, you also have to multiply the coefficient by the number of sodiums as well. So there are 2 times 2 sodium. That means that there are 4 sodium atoms. Now, as a result, in the reactants, this is no longer balanced. We have to change this coefficient to 4. So there are 4 sodium atoms in the reactants. 2 times 2 is 4 sodium atoms in the products. In the reactants, we have 2 oxygen, and in the products, we have 2 times 1 equals 2. So this is the balanced equation. 4Na plus O2 produces 2Na2O. This is balanced. Let's write a balanced equation for the reaction of copper in silver nitrate to produce copper 2 nitrate and silver. We'll start with all atoms that appear only once, and we'll treat polyatomic ions as a single entity, provided that they don't change during the reaction. So we have copper, copper, silver, silver, and nitrate, nitrate. Let's start with the coppers. In the reactants, we have 1 copper. In the products, we also have 1 copper. Next, we'll go with silver. In the reactants, we have 1 silver. In the products, we have 1 silver. So far, each of these are balanced. Next, let's look at the nitrate polyatomic ion, NO3. In the reactants, we have 1 NO3. How about in the products? In the products, we have 2 NO3. So in order for these two to balance out, we have to add a coefficient in front of the molecule containing nitrate in the reactants. So I'm going to write the coefficient 2 so that there are 2 nitrates. But remember, this now also changes the number of silver. So in the reactants, there are 2 silver. I need that to be the same in the products. In order for there to be 2 silver in the products, I will have to draw a coefficient, number 2, in front of the silver. So let's double check after we've done these changes. 1 copper, 1 copper, 2 silver, 2 silver, 2 nitrate, 2 nitrate. This is a balanced equation. We're going to look at different types of chemical reactions that are summarized into different groups. The first types are synthesis and decomposition reactions. Synthesis reactions are reactions in which 2 entities come together to form 1. Decomposition reactions are the opposite, where 1 entity decomposes into 2. They can be summarized in different sections. The first is a reaction of a metal oxide and water. This is when a metal oxide reacts with water and a basic solution results. And this is because the product is a metal hydroxide, which is a type of base. So in this example, calcium oxide and water come together to form a single entity called calcium hydroxide. A plus B produces AB. This is a synthesis reaction. Similarly, we have lithium oxide and water combine to produce lithium hydroxide. We also have reactions between nonmetal oxides with water. When a nonmetal oxide reacts with water, an acid is formed. In this first example, we have SO3 reacting with H2O, producing H2SO4. A plus B produces an entity, AB. Single displacement reactions are the next types of reactions that you will observe. One element displaces or replaces an element in a compound. And when this happens, it is because of the activity series. The activity series is a table of reactivity of metals relative to each other. The most reactive metals are on the top of the activity series, and the least reactive metals are on the bottom. Hydrogen is included in the series, even though it's not a metal, because it forms a positively charged ion, just like a metal would. The activity series is based on two important generalizations. One element can displace elements below it from a compound in a solution, but cannot displace elements above it. So the stronger an element is, the lower it is on a reactivity series, or the higher it is on a reactivity series, rather, the more capable it is of displacing an element that is below it on an activity series. And the farther apart two elements are on the activity series, the more likely it is that it will displace rapidly, quickly. To determine whether or not a reaction between an element and a compound will react, look at the relative reactivities of the two metals. If the higher, more reactive metal is the element, the reaction proceeds. If the higher metal is in the compound, no reaction proceeds. The general form for a single displacement reaction is A plus BC produces AC plus B. So what happened in this example is the element A, if it's higher in the reactivity series, will displace B, forming a compound with C. So B is displaced and left on its own. There are three types of single displacement reactions. There are those involving a metal and an ionic compound. For example, magnesium and copper sulfate becomes magnesium sulfate plus copper. The magnesium displaces the copper, and copper ends up on its own. We can have a similar example where the reaction doesn't occur. For example, lead and zinc nitrate. No reaction will occur because zinc is higher on the reactivity series, and lead is less reactive than zinc. We have reactions involving metal and an acid. So we have lithium and H2SO4. In this case, lithium is going to displace hydrogen, producing lithium sulfate and hydrogen gas displaced on its own. Again, we have the general formula: A plus BC produces AC plus B, where A is the lithium, B is the hydrogen, and C is the polyatomic ion SO4. So we can see that A displaced B and left B by itself. We also have reactions between metal and water. Sodium, we'll label it as A, and H2O, we'll label it the H as B, and the second H and the O as C. So we end up with AC plus B. And the reason why this happens is because sodium is highly reactive with water. We can also have a second group of single displacement reactions involving halogens. Still the same general formula, but these involve the displacement of halogens based on the reactivity. Note that fluorine is more reactive than chlorine, and chlorine is more reactive than bromine, and bromine is more reactive than iodine. So the single displacement pattern for halogens is slightly different from the pattern used for metals, and this is because a negative ion, an anion, is displaced rather than a positive ion. So in this example, we have chlorine and potassium iodide. Chlorine is more reactive than iodine. Chlorine is more reactive than iodine. So chlorine is going to displace the iodine and leave the iodine on its own. If it were iodine reacting with calcium bromide, no reaction will occur because bromine is more reactive than iodine. So no reaction happens. We'll next look at a specific set of reactions called combustion of hydrocarbons. There are two categories of combustion. The first is complete combustion. When complete combustion happens, that means there's enough oxygen present to make the products water and carbon dioxide. If there's insufficient amount of oxygen to make carbon dioxide exclusively, the products will then become water, carbon monoxide, and carbon dioxide. So in complete combustion, we only have two products, water and carbon dioxide. But if there's not enough oxygen, then we're going to get water, carbon monoxide, and carbon dioxide. For example, write the balanced equation for the incomplete combustion of C3H8, assuming that no CO2 is made. In this example, we can balance this equation we have 3 carbon on this side and 3 carbon on that side. We have 8 hydrogen on this side and 8 hydrogen on that side. We have 8 oxygen on this side and 2 plus 2 plus 4 is 8. For the complete combustion of C4H10, the balanced equation looks like this. 2 C4H10 plus 13 O2 produces 8 CO2 plus 10 H2O. So we have 8 carbon on this side, 8 carbon on that side, 10 hydrogen on this side, 20 hydrogen on this side and 20 hydrogen on that side, 26 oxygen, and 16 plus 10 is 26 oxygen on the other side. There are other combustion reactions. Technically, a combustion reaction is any reaction where one of the reactants is oxygen. But most combustion reactions are exothermic. They release heat. For example, we have the combustion of magnesium. Magnesium metal reacts with oxygen to produce magnesium oxide plus a lot of heat. Using a solubility table. The solubility table is always provided for tests and exams. And the solubility table tells you which ions are soluble and what exceptions exist. For each of the following compounds, determine the solubility of the following compounds. First example is silver nitrate. Let's find nitrate on the solubility table. Nitrate lies on the top half of the solubility table, which indicates very soluble, and there are no exceptions. So silver nitrate is soluble. Let's find out if barium sulfate is soluble. SO4 is very soluble unless it's with calcium, barium, strontium, mercury, lead, and silver. So since we have barium here, and it's one of the exceptions, then barium sulfate is insoluble. Next, we'll look at carbonate. Carbonate is not very soluble. It falls in the second half of this table. It's only slightly soluble, unless it's with group 1 ions or ammonium. Since carbonate is listed with ammonium, generally it's insoluble, but in this case, because it's with ammonium, it's soluble. Next we have lead iodide. Lead iodide is insoluble because it doesn't contain any of the very soluble halides or halogens. The only ones that are very soluble in the halides are those that are paired with copper, silver, mercury, and lead. So, a halide is very soluble unless it's paired with lead. So in this case, because the halide, iodine, is paired with lead, it will not be soluble. Next we have sodium sulfide. Sulfide is insoluble except with group 1 and group 2 ions and NH4. Sodium is a group 1, making this soluble. Now these solubility rules are really important in determining how double displacement reactions will occur, or if they occur at all. Double displacement reactions are reactions that produce a precipitate. How do you know if a product is insoluble? Well, we have to use the solubility table to determine. So will this reaction proceed? Let's take a look. We have silver nitrate and potassium chloride. Let's take a look at the products. Silver chloride and potassium nitrate. Will a reaction occur? It will occur because silver chloride, based on our solubility table, is soluble, and potassium chloride is soluble. Sorry, this is insoluble, and this is soluble. So what we formed here is a precipitate. If a precipitate forms, then this reaction takes place. Take a look at the next example. The potential products for this example would be iron sulfate and potassium chloride. Since both of these are soluble, no precipitate is formed. The ions will just remain soluble and separated, so no reaction happens. Remember, the only time a reaction is going to happen is if an insoluble precipitate is formed. Next, we have double displacement reactions that produce a gas. Sometimes a gaseous product is formed during a double displacement reaction. When it is formed, it escapes into the air as bubbles of gas. A common gaseous product is hydrogen sulfide gas. It's formed when an acid reacts with a soluble sulfite, such as sodium sulfite. Gases are also produced when an unstable product of a double displacement reaction decomposes. And this is a two-step process. Firstly, when a gas is produced, a double displacement reaction will happen. Next, let's look at this two-step process. The common unstable product to be watching for is H2CO3, carbonic acid that decomposes into water and carbon dioxide gas, and sulfurous acid that decomposes into water and sulfur dioxide gas. Example number 1. The overall equation is magnesium carbonate and sulfuric acid undergo a double displacement reaction to produce magnesium sulfite, H2O, and CO2 gas. The first step happens because we produce magnesium sulfate and H2CO3. But H2CO3 will decompose in an aqueous solution to produce water and carbon dioxide. So the overall reaction does not include this intermediary step, because this intermediary step decomposes to produce carbon dioxide gas and H2O. Let's look at the overall example between magnesium sulfite well, sulfurous magnesium sulfite rather, and hydrogen bromide. They would produce an overall reaction of magnesium bromide and water and sulfur dioxide gas. But this happens because of the intermediary step in which sulfurous acid is produced. If sulfurous acid is produced, then it will decompose into water and sulfur dioxide gas. So the overall equation looks like this. So what do we need to look for? The presence of carbonic acid or sulfurous acid. If this happens, we have an unstable product and the reaction decomposes. Look for these examples in your homework problems. Finally, we have neutralization reactions. These are when acids react with a base to form water and salt. Here we have an acid and a base producing a salt and water. If these are your products and these are your reactants, then what you have is a neutralization reaction. Please try any homework problems and LMS quizzes provided.